All right, so in this last section of Chapter 4 of these lecture notes, we're going to talk about what acceleration feels like and why it feels that way. And we'll also discuss the important question of what forces are acting when when we observe an object moving in a circle, right? When an object moves in a circle, its velocity is changing because the direction of its velocity is changing. So what forces do we need to exert on an object in order to get it to move in such a circular motion, right? So let's start out by talking a little bit about our experience of the feeling of acceleration. So this is 4.3.1 of the lecture notes, the feeling of acceleration. So, you may have noticed, for instance, when you step on an elevator and you hit the button and there's that brief moment where the elevator is first at rest, and then eventually it's going to reach a steady upwards or downwards velocity. But as it's going from rest to that velocity, there's a period of acceleration. And if it's accelerating upwards, maybe you've noticed feeling a little bit heavier, like you're being pushed down. When it's accelerating downward, maybe you feel just a slight feeling of, not weightlessness, but you weigh a little bit less, like a feeling of being pushed upwards. We all have, I think, this kind of intuition that comes from things like riding elevators or maybe driving over the top of hills very quickly, or as we'll talk about at the end of this section, like being on a roller coaster, where the whole point of a roller coaster is to kind of play with our feeling of accelerations and weightlessness and changing apparent weights as you get flown through different turns and spins and loops and whatnot. So great. So so far in this class, we've kind of focused on how forces generate accelerations. That's kind of the causal relations that come from Newton's second law of motion. You apply a net force on an object, that object experiences a rotation. There's a sense in which we can turn this around, right? If we see an object accelerating, we can infer that a force has to be pushing or pulling on it, right? So if you see the velocity of an object changing, or if your own velocity is changing, you know that there has to be some net force acting on it. And the details of how that force gets exerted, for instance, on you, ultimately determines what it feels like to undergo that sort of acceleration, right? So for instance, suppose you're sitting in a car seat. So here's a seat, or maybe here's a person sitting in a seat attached to a car, expertly drawn as always, and they've got arms and legs, and they're happy. Great. So if this car is moving at some constant velocity and not accelerating at all, for the most part, it kind of just feels like the bottom of the car seat is pushing up against you. If you're the kind of person that leans back in your seat, then, you're resting at an angle, and the back of the car seat is also supporting some of your weight. But if, like me, you always, I'll say, try to sit up and not say hunch over, because the first one sounds better. If you're like me and you never lean against the back of chairs, then, as you're driving at constant acceleration, constant velocity, the force of gravity is pulling you down, and it feels like the seat is pushing back up against you, right? Because that's how the seat is exerting support forces, so that you're not accelerating in the downward direction, right? Now, when you slam on the gas, your engine is converting some of the chemical energy in the fuel into rotational motion of the tires, which, because they're rolling along the ground, gets converted into forward additional velocity of your car. So that is going to make the car move faster, right? And the whole car is moving faster, so the car starts to accelerate in this direction, picking up more and more velocity. The car seat is, bolted to the car frame, so the car seat also starts accelerating forward. And the way you're connected to the car is through the seat, right? And so you start accelerating forward because there's an object that's exerting a force on you. And in this case, the object that's exerting a force on you is like the car seat, right? So, the car seat, the whole part of it connected to you, starts exerting a force in the same direction as the acceleration of the car, and you start accelerating in the same way that the car is accelerating, right? Now, somewhat remarkably, the feeling of this acceleration, the feeling of, having the car seat now pushing against your back, if you think about just that sensation, is the same as the feeling of gravity. So if I were to accelerate forward at 9.8 meters per second squared, I would feel the car seat pushing against my back in exactly the same way as if I was just lying on my back with no velocity whatsoever on that same car seat, right? There's a sense in which you might say, how could this have been different? If you're just standing on the ground, not moving, You know, we're standing motionless, so we're not moving, we're not sinking into the ground, we're not lifting up into the air, and we know that, you know, we are exerting our weight down on the ground, and the weight is supplying, and the ground is supplying some support force back upwards. And it's not like the ground knows what our weight is coming from. It's not like it knows that we're standing still, as opposed to, say, we're in the middle of jumping upwards. It's just exerting some support force necessary to keep us from not sinking into the ground, right? So when we're accelerating, the sensations that we feel are like our nerves detecting the external forces that are acting on us, as well as kind of the internal forces of like, you know, your bones and muscles and ligaments and tendons exerting forces on different parts of the body, right? Importantly, this is not a statement about like the fallibility of our biological sensations of the world. It's a statement about the nature of the physical laws of the universe. So a very famous kind of thought experiment imagines locking a scientist in a room, not in a room, let's say in some compartment, you know, and they can have access to as many lab supplies or fancy, you know, pieces of equipment as they want. So there can be beakers, there can be, like, I don't know, a pendulum. You can have whatever you want. And the thought experiment imagines asking, you know, locked inside this room and only able to make measurements with, you know, whatever equipment they want inside this room, can the scientist tell the difference between, let's say, being locked in a room somewhere on the Earth, you know, just experiencing a force of gravity, versus, you know, what if this whole compartment was strapped to like a crazy rocket ship in outer space, accelerating in this direction at the same rate of acceleration as what the acceleration due to gravity would be? Is there any way to tell gravitational forces from accelerations? And the inability to distinguish between those two things, between either there being a gravitational force or being in an accelerating frame of reference, a non-inertial frame of reference that isn't moving at a constant velocity, that's actually an example of underlying Einstein's equivalence principle. And this is one of the foundational Einstein's equivalence principle, one of the foundational pieces that underlies Einstein's theory of general relativity. Now, of course, we won't be getting into general relativity in this class, but the fact remains that the idea that like our feelings of acceleration are very hard to distinguish between what gravity feels like. Feelings of having a gravitational force exerted on you isn't just a statement about how we as humans experience the world. It's a statement about how the universe works, which I think is actually quite cool, right? So by thinking about how accelerations feel, you can kind of summarize some of what we've just talked about by talking about an apparent weight. So let's say feeling of acceleration, and we can kind of try to capture this by thinking about the apparent weight. Okay. So for instance, if we're just standing motionless on the ground and we're not accelerating at all, we know that we're not accelerating, and our apparent weight is just equal to the actual weight, our actual weight. So motionless on the ground, you know, if the acceleration is 0, then our apparent weight is just equal to the normal weight, the force of gravity, mass times the acceleration due to gravity. Okay. On the other hand, suppose rather than standing on flat ground, we're actually in an elevator that's going upwards, right? So when the acceleration is pointing up, we feel like we're a little bit heavier. So there's a sense in which the feeling of acceleration is pointing in the opposite direction to the actual acceleration. And in this case, so here, weight is equal to force of gravity is equal to, let me call this weight sub apparent. Here, you know, there's actually a force of gravity, there's actually an acceleration going up, and our apparent weight is equal to our actual weight plus, say, our mass times this, plus our mass times the negative of this acceleration. And so I should write that as weight minus mass times acceleration, right? So we're accelerating up, but we feel heavier, right? Similarly, if we're driving, you know, one of these days I'll learn how to drive a car, and draw driving a car, I suppose. If we're in a car accelerating this way, what is our apparent weight? Let me not draw the seat because that'll take forever. Gravity is actually acting in this direction. Acceleration is actually pointing to the right. We kind of have a feeling of being pushed back against our seat. So there's like this feeling of acceleration that points in the opposite direction of acceleration, and our apparent weight kind of points in this direction, both down due to gravity and against the direction of acceleration. So here, our apparent weight is equal to, again, it's like the force of gravity minus our mass times this actual acceleration, right? And similarly, you can work out, okay, if I'm, say, in an elevator, but now I'm going down, so my actual acceleration, let's draw it, I suppose. There's an actual acceleration of this whole thing pointing down. There's the force of gravity also pointing down. Here, your apparent weight is given by, your actual weight, this mass times the acceleration due to gravity. So this time, let's write it that way, m times g vector, minus our mass times acceleration. And where again, the acceleration here is in the same direction as gravity is pointing. And maybe now, you're starting to get a sense of why, when the elevator is accelerating upward, we feel a little bit heavier because negative acceleration points in the same direction as gravity. So our apparent weight is equal to, our mass times the acceleration due to gravity plus the magnitude of whatever our upward acceleration is. In this example, where we're accelerating downward, our acceleration is kind of making us feel a little bit more weightless, right? Acceleration and the acceleration due to gravity are now pointing in the same direction. So we feel as if our mass, our weight, is a little bit less than usual. And this kind of goes all the way up until, when you're, say, in free fall, and you have a sensation of being weightless. Your internal organs are no longer pushing and pulling on each other in the same way as if you were standing flat on the ground. And in fact, you can even go beyond that. So if you're accelerating downward, but faster than the acceleration due to gravity, then, rather than feeling weightless, you feel like there's gravity pointing in the opposite direction. It's kind of interesting. Okay, that's kind of the feeling of acceleration. We're going to talk about this a lot in just a moment as we talk about what it feels like to be on a roller coaster. But before we can talk about roller coasters, we need to talk about what it's like to go through a turn, right? And the simplest version of going through a turn is moving in a circle, right? So I would actually say we have a pretty good intuition just in our daily lives of what it feels like to accelerate in a straight line. The English language has these words, acceleration and deceleration, that we use all the time when it comes to, I'm moving at some velocity and I change my velocity, but in that same direction. So if I'm accelerating in colloquial English, that means I'm speeding up. And if I'm decelerating in colloquial English, that means I'm slowing down, but still moving in the same direction. And, in our physics language, we usually just say you're moving at some velocity. And if, your acceleration points in this direction, then your velocity will increase. And if your acceleration points in the opposite direction, your velocity will decrease, right? And it's just, what direction is the acceleration pointing in? Is it perfectly with the velocity or perfectly against the velocity? Okay. When I say it that way, though, it's kind of clear that, acceleration could point in any direction. It doesn't have to be exactly aligned with velocity or anti-aligned with velocity. I could say the acceleration is pointing this way, or this way, or, this way, or whatever. And if that doesn't correspond to just changing the magnitude of the velocity, presumably it corresponds to changing the direction of the velocity, right? So let's think about this in the context of simple motion at constant speed, just moving in a circle. And let's try to figure out what direction of acceleration corresponds to that kind of motion. So I'm going to do this in the context of, let's say, a playground carousel. So I don't know either if I can draw this or if you've experienced playing on one. So I've got like a pole connected to a platform that's able to spin because it's, sitting on some bearings or something. And, there's like these little handrails that a person could hold on to. So for instance, maybe I'm standing over here and I'm holding on to this handrail, right? And the whole thing has some angular velocity, let's say, that I'll write with this omega, right? So this is kind of a angled on side view. What does this look like if I just view it from the top? So from the top, I have, an approximate circle. It's rotating in this direction. And I've got my person, say, over here, spinning around in this circle, right? So first, what is the instantaneous velocity of this person, right? The angular velocity of this person is kind of counterclockwise, but instantaneously, the person is just moving in a direction that's like tangent to the circle, okay? So their instantaneous velocity is, say, at this direction. And if I have another person, say, sitting over here, their instantaneous velocity is in this direction, right? And so as you move around the circle, because this thing is rotating in a counterclockwise direction, the direction of the instantaneous velocity of these people is always changing, right? Which way is the acceleration pointing? That is to say, how is the velocity changing from one moment to the next as these people go around in a circle? One way to think about this is to think very carefully and use your knowledge of like geometry, maybe even a little bit of calculus to say, if I'm here and my velocity is pointing this way, and then I move just a little bit forward, and now my velocity is pointing, in a slightly different direction, tangent to the circle, like how much does this angle change? What direction have I changed in? And if I assume, I have a velocity that's pointing this way at this magnitude, and I draw just a hair further, and I have another velocity pointing in a slightly different direction, but with the same magnitude, how much has that velocity changed? What is actually the tiny, tiny change in direction of velocity, and then make an acceleration point that way? If you've taken calculus, that's something you could do. A kind of intuitive way you could think about it is, like, imagine swinging something in a circle. So here, I don't know how well you can see this, I've tied a, bicycle lock, gym lock, I guess, to a piece of string, and I can swing it in a circle over my head, right? So I can kind of start going, I can bash myself in the face with it. And here, I'm exerting forces to try to get it to swing in a circle, right? Now, I'm also exerting forces to kind of fight against the fact that gravity wants to kind of bring it down and make it hit me in the face again. But when it's swinging in a horizontal circle, the string, I'm exerting forces on the string, and the string is exerting forces on the lock to make it constantly change its direction of motion, right? Now, when it's swinging around, what direction can the string exert forces in? The string is just this thin, one-dimensional object. The only directions that it can exert forces are along its own extent, right? So if the string is like this, the only force the string can exert is in the direction from this lock to my fingers. And if it's over here, same thing. It can only exert forces in the direction of the string itself, right? What that intuitively should tell us, without thinking about the calculus of how much does the tangent to the circle change as you move along the circle, is that, the force exerted by that string is directly from the thing that's rotating towards its center of rotation, towards the pivot point that it's rotating around, right? So in fact, on this playground carousel, this person is exerting a force on this bar. The bar is exerting a force on the person too, of course, and the force is directed directly towards the center of this thing. So if this is the center of the circle, I've got a force that's acting perfectly in this direction in order to keep moving in that circle, just like the string was exerting a force directly from the object to the point that it was swinging around in order to keep changing its velocity. And we know that if this is the net force acting on an object, that also means that the acceleration is pointing in the very same direction. So force is pointing that way, and acceleration is pointing that way, right? And the relationship between force and acceleration is, again, force being the mass times the acceleration, okay? So that's something, I think, really cool that we're able to figure out, for instance, just by swinging stuff around in a circle. In order to move in a circle at a constant velocity, you need to have an acceleration that's pointing directly towards the pivot about which you're moving, okay? So this is all called uniform circular motion. Uniform circular motion. Circular motion because you're going in a circle, and uniform because we're talking about moving at a constant speed. And in this type of motion, that means that there's a force. So there is a force. To have uniform circular motion, you must have a force pointing towards the center towards the center of rotation, of revolution of the circle. And this force is called a centripetal force. And the word centripetal comes from Latin roots that just means seeking the center. And so it's an easy way to remember what this force is called, because you've got a force that's seeking the center. It's pointing towards the center of the circle that you're moving around. And that's how you get uniform circular motion. Okay. The centripetal force, it's not like a new type of force. It's just a net force supplied by whatever, me pulling on that string, or someone hanging on to a pole of a carousel or whatever, supplied by any of the things that we know can exert forces. The important thing is that in this case, it's pointed towards the center of motion. Okay, so it's not the centripetal force is not a new type of force. It's just a net force that points in a center-seeking way. Right? That's great. You might ask, so we've got this idea of a centripetal force, and we know the direction that it's pointing towards if we have uniform circular motion. What about its magnitude? Well, for uniform circular motion, the direction of the centripetal force is towards the center. What is the magnitude? What is the magnitude of the force? If you have a force that's not the right magnitude, you'll still turn, but you won't turn like in a perfect circle. Or maybe you'll accelerate as you turn, or change the magnitude of your speed as you turn. Of course, you'll accelerate as you turn. You see, it's the problem with the English language. So similarly, if I just start swinging this a little bit, there's a certain amount of tension that's being communicated through the string. And the tension on the string actually gets more and more as I spin this around. It also gets more and more as I spin it around faster and faster. I guess I should do it this way. I feel the string pulling against my fingers more and more as I make this go faster. I also feel the tension change as I change the size of the circle that it's rotating around. Right? So first, what I might want to ask is, we have this sense that the magnitude of the force depends both on the angular speed, what is the rotational rate of these things, but it also depends on maybe something to do with the distance away from the center of the circle that you're moving through. I might ask, think about pausing this video for a second, and just by thinking about dimensions, what are the dimensions of force? What are the dimensions of how fast the angular velocity is? What are the dimensions of how far away from the center of the circle are you? Well, this one should be pretty easy, right? By thinking about these three things, maybe you can use dimensional analysis to make a guess about what the answer to this question is. Just by dimensional analysis, what does the magnitude of the force have to be in terms of how it depends on these types of quantities? So pause the video for a second and think about that. Great. The answer. The answer is that if you have uniform circular motion, that corresponds to a certain amount of instantaneous acceleration, right? So in this picture up here, instantaneously, this velocity is pointing up, and in order to get this to go in a circle, instantaneously the acceleration is pointing towards the center of the circle. And over here, the velocity is pointing this way, and instantaneously the acceleration is pointing towards the center of the circle, A, B. And over here, the velocity is pointing this way, and instantaneously the direction of acceleration is this way. Okay. Well, if I think about the magnitude of this acceleration, this turns out to be, whatever your linear velocity is squared divided by the radius of that circle. And that's the same as what is the angular velocity of the rotation squared multiplied by this radius of the circle. So this is the formula that tells you the magnitude of the acceleration that you need in order to move in a uniform circular motion. And you know that that means the force, which is equal to the mass times the acceleration. The magnitude of the force is just going to be the magnitude of this multiplied by your mass. So mv squared over r, and that's the same as m omega squared times r. Really briefly, since we just talked about centripetal forces, you might be wondering about centrifugal forces. So, like aside, centrifugal forces, which maybe you've heard about. Centrifugal forces. For instance, if you're in a car and you make a tight turn while you're speeding down the highway or, going on an off-ramp or something, you feel like there's a force that's pushing you outward, right? So if you're turning this way, it feels like you're pushed against, maybe your car, the side of your car, like outward against the direction that you're turning. And so people often think that there's actually a force that corresponds to this kind of outward push as you're moving in a circle. And this turns out to be one of those caveats. Back when we were talking about frames of reference, we were pretty careful to say that if you're in any inertial frame of reference, that is, any frame of reference that is not accelerating, then physics looks the same. You'll agree that there's the same sets of forces acting on things, you'll agree that Newton's laws are obeyed, and you'll agree on all the kind of basic relationships between how things work, but you'll just disagree on some of the numbers. Okay? But remember that moving in a circle is not inertial. I wish I could say it was inertial, but I guess that's not an actual word. You, by moving in a circle, are constantly changing your velocity. And that means you do not have a constant velocity, right? You are always accelerating, again, in the direction towards the center of the circle. Okay. So when you're in a non-inertial frame of reference, you do not agree that the same set of forces are acting as someone sitting in a different, inertial frame of reference, someone sitting outside, right? So to you, it feels like there's this centrifugal force. You're in a accelerating frame of reference, and you feel as if there's some additional force acting on you, right? Someone standing off to the side, like the same thing holds in these carousels. You're moving in a circle, and you certainly feel like there's something pushing you outward. And that's why you have to hold on so tight in order not to go flying off. But, someone standing on the ground over here, looking at this whole thing, knows that it's not that you're standing, you can't think of yourself as standing still and experiencing a force pushing you outward. Instead, you're moving in such a way that you're constantly changing your velocity. And that means you need to be exerting a force pointing towards the center of this circular rotation in order for you to change your velocity. So these centrifugal forces are kind of like a fictitious force that feels like is acting on you when you are not in an inertial frame of reference, when you are accelerating, right? Great. Sometimes these fictitious forces are called pseudo-forces, which is just a fun word. But anyway, great. Now that we've talked about moving in a circle and the kinds of forces and accelerations that you go through, together with, we had this discussion of the feeling of acceleration and apparent weights, we can talk about roller coasters and what it's like to ride on one. I don't know, has everyone in class been on a roller coaster? They're fun, I think. They're fun to different people. Roller coasters basically, well, at some level are fun because they involve dramatic, often very rapid changes in your own velocity. And by twisting and turning and moving you through spins and making you go on loop-the-loops, a roller coaster is subjecting you to all sorts of accelerations. And that's playing with your apparent weight, the way that you feel like you weigh and the way your internal organs feel like you weigh, for that matter. Right? So for instance, when you fall, when you're in like one of those drop towers, right? One of those massive, there's a big tower and there's like a big disc full of people and you're all just hanging here, strapped in, hopefully. And this thing just suddenly goes into free fall. Right? As we discussed up above, we're accelerating due to gravity, and our apparent weight, this apparent weight, which is the actual acceleration due to gravity minus our mass times our actual acceleration. Well, in free fall, our actual acceleration matches the acceleration due to gravity, and we feel weightless and terrified, presumably. Right? What about when you go through like one of those loop-loops? Right. So, you've got a track that's sending your car down, and then there's like one of these, what does it feel like to go through one of these things? So, at this part, we've got these cars full of people. Yay. moving at some velocity, you know, what goes on as you go through this loop, right? So, at the bottom, again, you're moving on maybe a flat section of the track, and so, your apparent weight just matches your real weight, right? You've got the force of gravity pulling down, and, at this point, say you're coasting at a constant velocity, so you're not accelerating, and so that's what you feel like your actual weight is, right? But what about when you're going around the track, right? So like maybe when you're up here, what's everything that's going on? On the one hand, you've got the force of gravity that's still pulling you straight down, right? Your velocity is pointed in this direction. We know that if you were moving through this circle at a constant rotational velocity, if you were actually in uniform circular motion, your acceleration would point straight towards the center of this thing, which I don't know where that is exactly because I'm not good at drawing a circle. It would point in this direction. I think I meant to draw the letter F here. Maybe the force due to gravity. Sorry. If this is not a powered track, though, your acceleration actually doesn't point directly towards the circle because you don't move at a constant speed through the whole circle, right? Really, you've got some acceleration component pointing towards the center of the circle, but also pointing down. You kind of start to slow down as you go up the loop-to-loop. And so your acceleration kind of points in this direction, and your apparent weight, maybe points in this direction, the difference between Fg minus m times this acceleration. So this is like apparent weight, and this is like acceleration. What about at the top of this track when you're hanging upside down, hopefully not too long? Again, your velocity is pointed this way. Gravity is, as always, pointed straight down towards the center of the Earth. Now my acceleration, both in order to keep me moving in this uniform circular motion, and also to keep you moving in this uniform circular motion, is pointed now towards the center of the circle, and you feel either a little bit weightless, or typically you get driven through these loop-the-loops fast enough so that you're pressed against your seats. You actually feel like your weight is maybe pointed a little bit in the up direction. Like the magnitude of this acceleration might be more than sufficient so that you're not just feeling weightless, but you're actually pushed against your seat a little bit, and so on and so forth. You go to this part of the loop-to-loop. Yay. Gravity is pointing straight down. You've got acceleration that's pointing kind of down a little bit and towards the center a little bit, as you both start moving faster through the circle and changing your velocity to follow the circle. And so your apparent weight is kind of, somewhere out in this direction. Right? Great. So, this is kind of like a physicist cartoon of, roller coasters are fun because roller coasters are constantly playing with your sensation of what you weigh like. By moving you through, loop-the-loops this way, you feel your weight changing in these directions. By spinning you around a curve, you feel your weight changing in those directions. And by combining them and twisting you around, it's kind of this fun, disorienting experience in rapidly changing what your apparent weight is. Right? Okay, great. So that's fantastic. That's the end of this section, and it's the end of this chapter where we've kept the same core concepts that we've developed in the last few chapters, the idea of Newton's laws of motion and how they connect forces with accelerations, and how accelerations are related to velocities and changing velocities and positions. Those set of concepts, together with concepts of conservations, conservations of scalar energies and conservations of vector momenta, both linear and rotational. And in this section, we've kind of talked about expanding the set of things we apply those concepts to, things like spring scales and collisions and now roller coasters, and how by thinking still with just that same core set of principles, we can start to understand more and more of the world around us. Right? So we'll continue that kind of attitude as we look at more kind of mechanical, moving objects and motions in the next chapter.